All right. Good morning, class. Now we will move on. We can't be doing revision lecture on SR Latch every day. So this was the SR Latch. That's the basic DNA, right? And I've showed you again in 2 of the lectures. Remember, our lecture time is very valuable. We only got 3 times 50 minutes. 3 times 50 minutes. 50 minutes per lecture. So we don't have much time to go through each and every thing over and over and over again. All right. Okay. So this was our SR Latch. We had case 1, case 2, case 3. The circuit is very fussy circuit. It's a fussy circuit. It works well with the input 0, 1. 0, 1, it will give an output of 1, 0. Q is 1 and Q bar is 0. And it works well with input of 1, 0. So 0, 1 and 1, 0, the inputs are always fixed. No 2 problems about it. Right? With 1, 1, the answer changes, keeps on changing. The answer keeps on changing, and basically it depends, but the only thing good about 1, 1 is it gives the answer of whatever the previous answer was. Right? It gives the output of what the previous output was. So it's basically memory. Right. So, and the other case, 0, 0, we simply don't use it in our SR Latch. Right. So that's our truth table for our SR Latch. 0, 0 not used, 0, 1 it's set, that gives you output of 1, 0, or 1, 0 gives you output of reset, 0, 1, 1, 1 gives you memory or hold. Alright. Now remember, we're using some English words over here. So our truth table on the output side is not exactly technically filled. It's not technically fully filled in terms of 1s and 0s. We're using some words like memory, not used, and so forth. Then what we did was we took our SR Latch, we added a new line, new part of the circuit to it, and we added the clock line. So now we've got 3 inputs, the S, the R, and the clock. And that's how we implemented it. And we went through the truth table yesterday. So we go through the truth table. Basically when clock is 0, everything just goes into memory mode. And when clock is 1, the latch works the same way as before, except for everything is flipped around. Right? So instead of having 1, 1, 0, 0 not used, you now have a 1, 1 not used. That's because of the NAND gate. By the way, have you noticed we're using only NAND gates? What is the purpose? Why are we using only NAND gates? Well, basically we want to develop our SR flip-flop only using NAND gates, universal gates. Also, if you can use NAND gates, that means you can also use a NO gate. Yeah, you can also use a NO gate. Yeah? So you can also, so just write this down, find out about the SR flip-flop and the SR latch built using NO gates only. Built only using NO gates. Alright. So once we reach this point here, guys, there's the intermediate inputs, S star, R star, Q and Q bar is there. We're using the word memory. Now this is where the jump occurs. Right, this is where the jump occurs. The jump occurs over here where we have the truth table. Now we want to represent, we can't use the word memory, we want to use certain algebraic expressions in our truth table. Now in our earlier truth table upstairs, if you look at the upper half of the page, we're using words like memory, hold, set, reset, not used. Right? So what we're doing over here is we now convert that same truth table. We've got 3 inputs, right? And now we want to put it in terms of memory. What will be our, see, with memory there's always a previous state and there's a current state. So if memory is retained, right, if you remember, that means you remember what happened before, right? Or similarly, so the way to put it was Qn plus 1 and Q. So Q is current, Qn plus 1 is, right, future. Or another way, if Qn plus 1 is now, Qn is before, right? So basically we're looking at the next iteration, what will happen in the future. So you've got 3 inputs. Now we want to put our truth table in terms of Qn plus 1. What is happening to the memory in the future, right? What is it remembering? So now if we, in terms of memory, if it recalls something, it's recalling a past state. It will always recall a past state. So Qn plus 1, with clock 0, it's always in memory mode. Therefore Qn plus 1 will remember Qn. it goes one step back. It always remembers what was immediately in the past, the immediate past, right? With clock 1, S0, R0, it's in memory mode. So the moment it's in memory mode, it remembers immediately what was in the past. Now, with SNR01, that's a fixed answer. Remember this, we said, hey, this is a fussy circuit. There's only 2 times when it gives a fixed answer, right? So that's when SNR are 01 or 10. So with 01, we get 0. So whatever Q was, we get the same. And whatever with 10, so line 0, 1, 2, the line 01 and the line 10, the clock is now 1, right? We'll always give a fixed answer as per your thing. But we are only giving what your Q was, because Qn plus 1 will remember what your Qn is. Alright? Okay? Your Q bar is there as well. There's also something known as the Q bar n plus 1. Right? Qn plus 1 bar. Right? But we're only focusing on the Qn plus 1. So that will remember what your Q was. Right? Which was 1. And that's from your upstairs. Now 1, 1 is still invalid. Right? That's from your SR flip-flop. Okay. Now let's move to the next step. Now based on this half, based on this table, we now draw a new truth table. And this time this is called the characteristic table, the SR flip-flop characteristic table. We draw a new truth table. The new truth table is based on the previous. So can you see how we're evolving? We had the SR latch table. After the SR latch, we modified the circuit, we came up with a new truth table for the SR flip-flop. So there's SR latch, there's SR flip-flop. From the SR flip-flop, we now redrew the truth table, which is now called the truth table in terms of Qn plus 1. What's happening to Qn plus 1? Then, now we have got a new table called the characteristic table. Characteristic table does not bother about clock anymore, right? Okay, it does not bother about clock. It's only looking at what is our current state and what is our future state. Or what is our previous state and the next state. Previous and next. Right? So Qn could be thought of as previous. Qn plus 1 is thought of next. Right? So just note this down. We'll try and use that terminology. Qn is previous or current, and Qn plus 1 is next. Right? Okay. So what we did was, from the upper table, we now have this new input of Qn, and we now want to look at everything in terms of Qn. So this is not a physical input. This is, we are just drawing the scenario that, hey, if Qn was 0, what happens? Alright? So basically, if we populate our truth table, like, because we've got 3 inputs, we populate our table 0, 0, 0, 0, 0, 1 all the way till 1, 1, 1. Right? So this side is done as per normal. The right hand side, Q next, or Qn plus 1, they call it Q star. That is done by doing this. So SNR is 0, 0. Just got to place this on the side over here. All right. Sorry, place this on the side. So look at this one. So if SNR are 0, 0, right, the output shall always be, if this is 0, 0, the output shall be Qn. Qn plus 1 will give you Qn. So Qn plus 1 will give you Qn. So Qn plus 1 is equal to Qn. And where do we get this table from? We are extracting it from here. So basically, we're doing a bigger form of this table, but this time we've got Qn on the input side. Right? Okay, so let's now look at 0, 1. How can I do this? I can do this. All right. Okay, let's have a look at this way. There we go. Okay, I hope you can read sideways. All right. 0, 0. Let's look for 0, 0 here. 0, 0. Right? 0, 0 gives us what? Qn plus 1 is equal to Qn. Right? Qn plus 1 is equal to Qn. So 0, 0. Qn plus 1 should equal to Qn. What is Qn? It's 0. 0, 1. Let's come here. 0, 1. Qn plus 1 is equal to 0. Outright. Just write down 0. Why is it equal to 0? Well, 0, 1 is one of those inputs into the truth table, into the flip-flop, which has got a fixed answer. It doesn't rely on memory. It's not memory mode. Memory mode only happens in 0, 0. All right. Okay. Now, 1, 0. Hey, 1, 0 is a fixed answer. 1, 0, fixed answer is 1. Fixed answer. We don't need to look at memory. That's set. Okay. Now, 1, 1. Hey, 1, 1 gives an invalid. That's an invalid mode. 1, 1 invalid mode. So we can't write down invalid. We want to move away from these words of invalid, memory. We want to put an algebraic expression now. What is Q1? So we simply don't, we say we don't use it. It's not used. So we say X. We're not even going to read it. Okay. Now let's move to the next one. 0, 0. 0, 0. Qn plus 1. This line here, Qn plus 1 is equal to Qn. So 0, 0. Qn plus 1 will equal to Qn, which is 1. Right? So you can write over here on the side, Qn plus 1 is equal to Qn. And same thing goes somewhere around over here. Qn plus 1 is equal to Qn. All right, now, next one, 0, 1. 0, 1 is a fixed mode, fixed answer. 0, 1 and 1, 0 always gives fixed answers in flip-flops. So, fixed answer. 1, 0, fixed answer, these two. 0, 1, fixed answer, 0, 1, 1, 0, fixed answer. 0, 1 gives you 0, 1, 0 gives you 1. Right, because memory will depend on the fixed answer as well. All right, now let's do this one here, guys. 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, invalid. So we put a X. Right, everyone happy with how I got that? Okay. Now that truth table is very long. We reduce it. There's now, okay, so what is the, what are we doing here? This particular table, what does the characteristic table give us? Characteristic table says that, hey, if you have the following thing stored in memory, if the following value is stored in memory, because remember, what is the purpose of a flip-flop? One flip-flop stores 1 bit of memory. It stores 1 bit. So basically coming down to it, this circuit, in summary, if you missed 1 or 2, if you've missed Monday's lecture, this circuit stores 1 bit of memory. Inside it, it is storing 1 bit of memory. Okay? Alright? It is holding 1 bit of memory. Okay. And the different commands, if you want to change the memory, if you want to insert a 0, so now if you want to insert a 0 into that memory bank, so it's a memory bank for 1 bit. You guys have big memory banks. You have, you know, those hard disks which come with, okay, your mobile phone comes with, how many? Like 2 gigabytes of RAM or something? Yeah? Okay, but if you want to insert something, you just upload the file into it, right? So over here, if you want to upload, let's ask an easy question. If you want to upload the bit 1, if you want to upload 1 into this, if you want to store it, right? Store 1 into this circuit, what is the configuration? What should we give in S, R, and 1? Right? So what are we going to do? We look at Q. Q is current memory. We want to store 1 in Q. Right? Over here, look at my pen. We want to store 1 in Q. So therefore, our clock should be 1. Our S and R should be 1, 0. S should be 1, R should be 0. Right? And that will store. On the other hand, if we want to store the bit 0 in the memory bank, in this memory bank, well, clock should be 1. We know clock should be 1. In order to do any changes, the clock has got to be 1, right? Okay, and our thing will be 0, 1. S will be 0, R will be 1. Right? Okay, can you see it's opposite of Latch. All right, now, what if you want to recall the memory? If you want to find out, hey, this is my memory bank, I want to find out what's stored there before. What are you going to use? Clock should be 1, and our memory should be, our S and R should be 0, 0. Or you could just make clock 0. It'll show you whatever. Just make clock 0, everything, whatever is inside will show up. Okay? Set. And of course, there's one line which we don't use. We don't use the invalid line. We design our system in such a way that those 2 bits never appear there. Okay? Alright. So that's our memory bank. So this was our characteristic table. So characteristic table is basically saying, is this, that you've got something stored in memory, right? And basically, we want to recover for the characteristic table, we want to recover. It's more about memory retrieving, like reading the memory. Characteristic table is to read the memory, right? So if your Q was this, and your S was 0, 1, whatever it is, and R was this, what is the memory going to show? What is Qn plus 1 going to show? Okay? Alright? So if what was stored before and your current two configuration, 0 and 1, 0 and 1 is like your buttons, like RCL and all that in your, or shift and RCL, you know, like in your calculator you use what, shift and RCL or something, right? Shift, so S and R you can think of it as shift and RCL, those are the two buttons you're going to press, and Q is whatever was stored there before, and Qn plus 1 will automatically show you, oh, this is what is there, right? Okay, so this is your truth table to retrieve the memory. Alright, now excitation table. So characteristic table, you can think of it in terms of a calculator trying to retrieve whatever is inside, right? Trying to open the flip-flop and say, hey, oh, 1 is stored here or 0 is stored here. Remember, it can only store 1 bit, either 0 or 1. But remember, 1 bit, from there you build 8 bits, you make a byte, and from there you build maybe 1 million of those bytes, and 1 million, you make 1 megabyte, right? Okay, or if you do 1 billion, then you will get 1 gigabyte. Alright? Okay. So, excitation table is the other way around. In excitation table, we take our characteristic table and we just rewrite it. Excitation table is this way. That hey, my memory right now has got a 0, but I want to change it to a 1. I want the memory, it's got a 0 now, I want it to change to a 1. What is the input which I should feed into the flip-flop to change it to a 1? You see what I'm saying? It's like the other way around, it's reverse. Both of the tables store the same information. Of course, we just rerouted everything and just rewrote everything in the same way. But what is the purpose? Excitation table is, what should I do? What buttons should I press on my calculator so that this value will change? Yeah? Okay? Right? So my memory, it's all playing with memory. My memory Qn is current. My memory has got this value, it's got a 0 or a 1, but I want it to have this. What should be my SNR be? So let's look at line number 1 of the excitation. My memory has got 0, line 0, sorry. My memory has got 0, I want it to still store 0. So what should be my SNR be? So S should be 0, R can be X, can be anything. Now, second line, line 1. My memory has got 0, but the next round, I want to retrieve a 1. I want to change the memory inside so that it will become 1. What should be my input be? So it will be a 1, 0. Line 2. My memory has got 1, but when I retrieve, I want to retrieve 0. What should be my SR be? It will be 0, 1. My memory has got 1, and I want to retrieve 1 again. Yeah? So it will be, S will be don't care. You can plug in whatever you want, but R has got to be 0. So everyone understood that? And over here, characteristic table is my memory has got this, my SNR is this, right? It's not predicting, it's not finding out. You already know, oh, now S is this, R is this, and my current memory is this. What will be showing in my next round? Yeah? Okay. Alright guys, now, let's now come to the next step. The next step, guys, is right from here we can put this in the form of an equation, Qn plus 1, and how did we retrieve that equation? We retrieved it using this. Qn plus 1 is equals to S or Q R bar. Just give me a second while you guys absorb this particular, how I got that. I give you a chance if you missed out yesterday's lecture. I give you a chance while I log on to the, oh sorry, freeze. I'll give you a chance while I log on to the Moodle shell. I just want to show you some things. Exam papers are stored where? I'll just show you something which will be in your exam. because I'm writing the exam right now, or well, pretty much done, and it'll have 70 marks worth of this, or 65 or somewhere around there. Library, exam papers, exam paper link, and 2018. Is there a way to do search over here? Does anyone know how to do search? Semester 1. How can I search this guy, man? Is there a search line over here somewhere? Hey, does anyone know this? Where? Here? Sorry? Oh, right, set, okay. Right. Okay. How do we search this? Oh, just scroll down, right? Right, this is last year's paper, eh? Guys, I want to share with you one particular part of the paper which will be coming line for line, because this is a hard topic, so I want to help you out. So this page here, that will be there, right? So I'm copying this line. I've changed this line here. It's 2019 now, but this page is coming. All right, guys. Okay, so this page is important, all right? What I'll do is I'll upload that onto the Moodle shell as well. These are 4 different types of flip-flop. What I did was I held your hand, and I'm going to show you how to do design using one flip-flop, because one flip-flop takes about 2 weeks or 2-3 weeks to do, right? Okay, but the good news is, you don't really need to learn by heart. You need to understand at least one, the fundamentals. If you can understand the fundamentals for at least one, right? SR is an easy one. If you can understand the fundamentals for at least one of the flip-flops, there's 4 flip-flops. There's 4 flip-flops, 4 different types of flip-flops. And your exam has all 4, right? Different. So there's something called the D flip-flop, which is the data flip-flop. The JK, I don't know why they named it JK, right? SR was set, reset. T is toggle. Right? So these are the 4 flip-flops: D, JK, SR, and T. All right. Now the key point is this, guys, that these tables. Can you see this table here? The table over here in the middle is the excitation table. The characteristic table. That's the characteristic table, like what we've done in our notes, right? S, R, and Q. The lowercase q that's the notation I just want to show you. That Q is Qn, and Q star is Qn plus 1. All right, Qn and Qn plus 1. All right, so sometimes they use Q and Q star. Okay, all right. And if you look at the bottom right-hand corner, you have the excitation table. So these tables will be given. You don't need to cram it, right? All these tables will be given. The important part is, at least you know the background of you. As engineer, you can't be using some table blindly. You must be aware of how those tables were derived. So what we've done in this Monday, Wednesday, and today's class is we were deriving this table for one of these. Now on the left-hand side is the circuit diagram, the standard circuit diagram, which is used for a particular, a flip-flop. That's an SR flip-flop. Now have a look at this. Have a look at the D flip-flop. Let's show you the D flip-flop. The D flip-flop, there's only one input. One input plus two outputs. Always you get a Q and Q bar. Can you see in all the flip-flops, you have a Q, you have a Q bar. Q bar, and guys, what is this line? That's your clock line, right? They've put a bubble in there, but luckily for our case, the bubble just means you're flipping over the clock, all right? The way which we've learned it right now, there's no bubble, right? But bubble, all it does is it flips everything around. Okay. QQ bar. This one, there's two outputs, QQ bar. SR is two outputs, QQ bar. T is two outputs, Q and Q bar. Right? Okay. Now, that's your characteristic table. That's your, what is this? This is your excitation table. So, can you see there was only one input over here? One input. Right? And I'm going to show you how we get that. Maybe I'll teach you two flip-flops. But before we move to that, I just want to go and, so we'll just move to the screen again. I want to show you, let's do a problem. The best way to learn in this particular situation I don't know how management came on. Okay. All right. Let's show you a real circuit. And by the way, guys, the other thing I want you to really brush up on is this particular tutorial. Right? If you are struggling with this tutorial number, the tutorial on encoders and multiplexers, please go and see one of the tutors, one of the TAs, see one of your friends, come and ask me, alright. It's a simple tutorial, but it's based on the lab. And one thing you could do is, if you go this week Friday, what I'll ask those, because I know most of the labs, this week there was no new lab. Last week's lab was difficult, so we extended it. And last week's lab was almost like a tutorial question, a full-on tutorial question, except you had to design it. So this Friday, from 1 till 4, the labs, those two lab demonstrators will be there to help you with any problems. They're like a tutor. It's like an open tutorial. We'll use the lab for a 3-hour tutorial session. But it won't be that they'll be on the board. You go to them with your question and they'll help you out. Right? Friday from 1 till 4 and also Friday from 9 till 12. So that's 6 hours. From Friday from 9 till 12 and Friday from 1 till 4. You guys just walk in. Go in, especially 1 till 4, there'll be 2 tutors available. From 9 till 12, I'll check, I think only 1 will be available. But you go in with your questions. If you're struggling with this tutorial, go ahead and get this done, alright? You've done the tutorial already. You just had a tutorial from 9 till 10. Another group had it from 10 till 11. If you're struggling, go ahead and do this, because this sort of problem will be coming in the final exam. Okay, now let's come back here. I'm looking for a circuit. We're going to come back to this, guys. The way the notes is written, the notes are basically, you see, sequential logic is taught in different ways, right? So the way I teach it, I start off from the latch, then I teach you the flip-flop, then I teach you the characteristic table, the excitation table, then we move to the state diagram. So what we're going to do now is we're going to move to the state diagram. This is a state diagram. Okay, now let me just give you a practical sort of visualization of a state diagram. So let's say A, B, and C are 3 traffic lights. Red, green, and orange. Right? Okay. So basically what it says is, if it was red before, the next state, if the input is a particular input, right? If you look on the line, that's the particular input, then it should change to green. Okay? So I will go through an exercise about this. So that's what we are moving to the state diagram. Now, there's 2 things over here. There's 2 types of problems. This here is the state table. Right? So we still not finished with tables yet. We're finished with characteristic table and excitation table. And those are fixed for your 4 truth tables. And they will be given in your final exam. Right? You will have to use those tables, the excitation table and the characteristic table, one of the 2, depending on the problem. If you are doing a design problem, if you're doing design, if you are asked to build some traffic light or calculator or some memory system, if you're asked to design, then we will use the excitation table. If you are if you want to analyze, if some circuit is given and you're asked to analyze, we'll use the characteristic table. Okay? Right? So let's show you a problem now. See, so they go through all the different flip-flops, all the flip-flops, flip-flop, flip-flop. Okay, all right, this is the next one over here. Okay, let's do this problem. And you'll get something similar in your final exam. You'll get two flip-flops, right? And they'll be hooked up. So this is the given circuit. We want to know what our X is. And I'm deliberately using the D flip-flop because we've learned the S and R, but I'm going to show you how we use the table. Okay? Okay. Right. And later on, as we get time, I'll show you how the D was developed. And it's the same concept. Okay. Now, let's look at this. Okay. Now, this is on the moodle shell. There's two flip-flops. The flip-flop on the left, let's call it flip-flop number 1. The flip-flop on the right is flip-flop number 2. Set? Everyone happy? Okay, we just label that. Right, okay. Now, there is one input called the X. One input called X. Yeah? Okay. All right. Now, let's have a look. Can you tell me what is the input into D of the first flip-flop? The answer is there already at the bottom. You can see it, but I want you to trace it. Now, what is the input into that OR gate which is connected? Can you see for the first flip-flop, flip-flop number 1, there's an OR gate connected there. And to the OR gate, there's some AND gates connected. Yeah? All right. Now, what is the input into the OR gate? So let's do some tracing now. What is the input into the OR gate? The input into the OR gate, the upper input, is the AND gate. All right. What is the input into the AND gate? Okay, so let's follow the line. It's Q1, right? Q1. And what's the second input? Z. Yeah, I'm looking at AND gate number 1. Once again, let's look at flip-flop number 1. We want to find out what is D. Right? So, we want to find out what is D equal to. What is being fed into D? What is your input into D? All right. So, let's do some tracing. So, the OR gate is connected to two AND gates. So, let's look at the first AND gate, the upper AND gate. The first AND gate is what? Z and Q1. Yeah? Z and Q1. Why do we say Q1? Because it's the flip-flop number 1. Z and Q1. Right? Just note that down somewhere. Z and Q1. Now, what is the second AND gate? The lower AND gate. That's X and Q1 bar. X and Q1 bar. Yeah? Everyone happy with that? So, finally, what is D equal to? What is being fed into D? The output from the OR gate. D is equal to, what did I say for the first one? I forgot it already. Z and Q1 brackets and, O sign, X and Q1 bar. So have a look at D1. Can you see what D1 at the bottom is? Yeah, right at the bottom you can say, hey, but there's something different here. Maybe I looked at it differently. Oh yes, sorry. Z is also equal to Q2 bar. Right? Z is the total output of the system. It's not an input. Right? Okay. All right. You guys got everyone with me here? We're doing analysis of a flip-flop system. Okay. Now let's look at D2. There are two flip-flops. We have to find out what are the inputs into those two flip-flops. So the input into D1 is, we just found out the equation. Let's look at D2. Right? Let's keep the answer covered and then we'll check it out later. Right. D2 is flip-flop 2. Right? And you can bring out your pen and write it down. This circuit is on page, page 12. All right? Page 12 of the note. Okay. Let's look at D2, guys. There's an AND gate there. What is the first input into the AND gate? If I'm correct, is that an X? X and Q1. Yeah, X and Q1. X and Q1, right, is equal to D2. Right. Now, what's the third thing we want to find out? So, we found D1, we found D2, X is fed, that's a system input. What is Z equal to, guys? Z is equal to Q2 bar. That's the output. Right? Okay, so this is some circuit. It may be some kind of triggering system for the alarm or something like that, right? It remembers how many times somebody went in, then they can't get out or something like that, right? Okay, latching system of something. So you've got three equations. You've got the equations of inputs into your flip-flops. You've got the equation for your output Z. All right. Okay. But hey, what is Q1 and Q2 bar and all this? How are we going to calculate that? Which table will we use? The excitation table or the characteristic table? We've been given the input. We want to find out the output. The characteristic table. Right? Okay. Excitation table is the other way around. Okay. So we have to do one flip-flop at a time. Flip-flop number 1, we know what is D. How do we know? We know from the equation. But we want to find out what is going to be the output. So let's move to the next line. Okay. Okay, we'll come back to this. We'll draw the two table again. All right, I'm going to do it on the thing to show you how we go step by step. Let's do the equations for this line, for this circuit. All right, because right now we all want to master how to get the equations. Once again, we're doing analysis. This is not a design problem, by the way. There's two types of problems. One problem is analysis. Analysis means you are given a system, you find out the behavior of the system, right? What's design? Design is the other way around. The behavior is given, you are required to draw this, make the circuit, build the circuit, right? Over here the circuit is given, we want to find out the behavior. What will Z equal to when X is this, and there's only two inputs, X and clock. Alright, okay. Now let's have a look at this circuit here. It's a JK flip-flop. It's a JK flip-flop. You have two outputs, two flip-flops, flip-flop A and flip-flop B. Same as saying flip-flop 1 and flip-flop 2. That's alright. Flip-flop A and flip-flop B. Your Q is A and A bar, Q bar, and B and B bar for flip-flop B. Alright, now let's have a look at flip-flop number 1. What is being fed into J? J is equal to? JA is equal to? X. What is KA equal to? Let's trace KA. It's X and B bar. Right? X and B bar. What is JB equal to? JB is equal to X or JB is equal to X or A bar. And KB is equal to, what is KB equal to? Same. Yeah, same answer. Right? X or A bar. Yeah? X or A bar. What is Z equal to? Final thing is Z. Not only are we looking at the inputs and outputs of the system, we are looking at Z as well. A or B. Right? Z is equal to A or B. There we go. Okay. All right. Now, let's now draw our state table. Which one do we want to do? Let's do the one earlier. So the first step is we're doing this sort of problem. We're doing an analysis of sequential system. We're doing an analysis problem. Right, so all our three equations. So we're doing an analysis problem. Okay. Now, problem on problem on page number 12. All right. Okay. So first step we do is we just write down those equations. D1 is equals to Q1 and Q2 bar or X and Q1 bar. D2 is equals to X and Q1. Z is equals to Q2 bar. Right? So we write down those equations. The next step, and there is going to be a slight problem because we have learned on doing everything using the clock, not bubble. So we'll just follow our own one. The next step, guys, is to draw. So step one, find the equations for all flip-flop inputs and the overall system output. Yeah, step one. So that's what we did. Yeah, we've done that. There was two inputs. Yeah. So there were two inputs. There were two flip-flops, and there were D flip-flops. So we used the D flip-flop. All right. Okay. And there's only one input for each D flip-flop, and there was one overall output. Okay. Now. Okay. Now, step two. It is what is called the state table. The state table. All right. How are we going to do the state table? Let's show you. Okay. So the state table is like this. You have two flip-flops. We start off with the current one, Q1, Q2, input X. These are inputs into our system. X is a physical input. And Y is X is our physical input, and Y is, and Q1 and Q2 are the states of the memory. So maybe I should just note that down. This is our present state. Present state. Okay? And X is the input into the system. Now, the next thing is we want to find out the future state. Want to find out the future state. The future state is, in this case, it'll be Q1 star, or maybe Q1 n plus 1, Q2 star. It's easy for me to label this way because then there's another thing. All right. Okay. Now, maybe I should have put, or maybe I correct that. Let's say D1, D2, right? D1 and D2, and Q1 star Q2 star, right, D1, D2, so that we put it in order. And then eventually you have an output. You have an output. Okay. All right. Now, input side. You have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. How do we find D1 and D2? How do we find D1 and D2?